everyone. Myself, Dr. Khalistan. I'm working as an assistant professor in the Department of Physics, Central University of Kashmir, and currently the coordinator of the department as well. So currently, I will be just delivering a talk for our integrated based MSc 4 students. So it's for the undergrad students. The subject is modern physics, and the topic I'll be introducing to them is I will be just giving them the introduction regarding quantum mechanics. Now, as you know, the quantum mechanics is one of the branches of physics, like we have other branches of physics, like we have thermodynamics, we have electronics for that sake, we have the nuclear physics, we may have the optics and all that. So quantum mechanics in similar context is one of the branches of physics. Now the point is, what does quantum mechanics deal with? Now, if we talk about the kinematics in general, we say kinematics is a branch of physics where we talk about the motion of a particle. Then comes the mechanics, because obviously the quantum mechanics is one of the branches of mechanics. In mechanics, what we do is we talk about the motion of a particle as well as we take into consideration the cause of motion as well. Now, what is the cause of motion? That's force. So in mechanics, what we do is we talk about the motion and its cause, that's force. Then, if we further divide the mechanics, we may divide it into classical mechanics, we may divide it into quantum mechanics, then we may have the relativistic quantum mechanics and all that. Now, what is the distinction between classical mechanics and quantum mechanics that we are going to introduce in this very lecture? Now, if we talk about let's take the example of the Bohr's model of hydrogen atom. Bohr's model of hydrogen atom was one of the interesting breakthroughs in the modern science, where Bohr's atomic model discussed about the atomic limbs of an atom, how the electrons transit from one shell to another shell and all that. But this Bohr's model of hydrogen atom were also having certain serious limitations. The serious limitations in the sense, we have Bohr's model of hydrogen atom available for the hydrogen or hydrogen-like atoms. Hydrogen-like means we may have helium positive, we may have helium divalent positive, means for those atoms which have single electron. Now, the point is, why don't we have the atomic model for the rest of the atoms? Means, why don't we have the atomic model for the helium atom? Why don't we have the atomic model for the carbon atom or oxygen atom, all that? So, this is one of the limitations of the Bohr's model of hydrogen atom. That if Bohr's model of hydrogen atom is applicable to hydrogen or hydrogen-like atoms, why it isn't applicable to the other atoms? That's one. Second limitation we can think about the Bohr's model of hydrogen atom is that in case Bohr's model of hydrogen atom doesn't in fact tell us about the fine structure lines we obtain from the hydrogen spectrum. And third, Bohr's model of hydrogen atom also doesn't give us any information why certain transitions are more possible or more probable compared to other transitions. Now the point here is, we don't want to present the Bohr's model of hydrogen atom in an unfriendly way. Obviously, the Bohr's model of hydrogen atom needs to be given due credit as it provided the breakthrough in the modern science. But the point is, means there is certain things are missing. Why couldn't the Bohr's model be applicable to other atoms? Why couldn't the Bohr's model explain us the fine structure of the hydrogen atom? Why couldn't the Bohr's model convey us any information regarding why certain transitions are more probable compared to other transitions? Now, all these, if you see the timeline, if we talk about in 1900, I'm talking about the timeline how we reached the quantum mechanics. In 1900, Planck gave the this quantum hypothesis. Then in 1905, we talked about the Einstein who tried to use this Planck's hypothesis, Planck's quantum theory in order to explain the photoelectric effect. Then Heisenberg came in around 1927. He tried to explain the uncertainty principle. Heisenberg also gave one of the profound explanation regarding quantum mechanics, where he tried to present as the matrix formulation of the quantum mechanics. Then obviously the Schrödinger gave us the wave equation system for explaining the quantum mechanics, and obviously then the Dirac also gave us the Dirac equation. Klein-Gordon came, they also presented their formulation of the quantum mechanics, and this continued further. Now the point is, what is quantum mechanics and how it is different from the classical mechanics? That's actually the main point to be discussed in the current lecture. Now see, as far as the classical mechanics is concerned, classical by word we say about old, which is comparatively old. So the classical mechanics was mostly based on the Newton's laws of motion and all. In classical mechanics, the essence of the thing is, in case the future of the particle can be predicted if we know the momentum and forces acting on the particle. Means if we have the particle, we know about the position of a particle, we know the forces acting on the particle and momentum consideration of the particle, we can predict with certainty the future of the particle. But the same, unfortunately, is not true in case of quantum mechanics. Means obviously we'll have observables in quantum mechanics as well, but the future of a particle, in spite of knowing the cause and effect, but can still not be determined in the quantum mechanics. So the essential difference between the classical mechanics and quantum mechanics here comes that in classical mechanics we can know the future of a particle if we know the cause, the force, the momentum of the particle at present. But in case of quantum mechanics, the future of the particle cannot be predicted with certainty. And what we do is we talk in terms of probabilities there. So now the reason is why we can't determine with certainty the position and momentum consideration of a particle in quantum mechanics. And the reason was given by the Heisenberg. Because you don't have Heisenberg's uncertainty principle between the position and the momentum. It states that we cannot predict simultaneously measure the position and momentum of a particle with accuracy. If you want to measure one quantity with more accuracy, the other will become less accurate. So in quantum mechanics, since obviously the quantum mechanics will deal with the atomic level, and the Heisenberg's uncertainty principle, although it is applicable both to the macroscopic as well as microscopic world, but because of larger mass of the particles in macroscopic objects, it doesn't seem to be appreciable. It seems to be appreciable only in case of microscopic objects, although it's applicable both to microscopic as well as macroscopic objects. So in quantum mechanics, while we deal with the atomic realm of the object, the problem becomes you don't know exactly the current position of a particle with certainty, because if you want to know the current position of a particle with certainty, the momentum will become less accurate, and if you are not certain about the current position and current momentum with accuracy, you cannot predict the future of the particle. So in quantum mechanics, what we did is we will talk about the probability. So the distinction between the classical mechanics and quantum mechanics, we can give that, while as in case of classical mechanics, you can predict the future of the particle provided you know the current position, momentum and the forces acting in the particle, while the same is not true in quantum mechanics. We just deal in terms of probabilities. Now, the first essential thing which we need to deal with in the quantum mechanics is what we call as wave function. And obviously wave function is a Greek term, we denote by psi. P-S-I, we denote it by psi. So whenever you are interested in studying the quantum mechanical behavior of a particle, what we need to determine is this wave function psi. Now, what is this psi? If we try to define this wave function psi, we may define it. It's the first thing, the wave function, it's a complex quantity. It's a complex quantity. This wave function itself has no significance. But if we take the square of this wave function, now this square of the wave function gives us the probability of finding a particle at a particular position under the given circumstances. So whenever we are interested in studying the quantum mechanical behavior of a particle, mathematically what we are studying is we are interested in finding the wave function psi of a particle. Now what is this wave function? As we discussed that, wave function itself is a complex quantity. It may not have a physical significance as of its own. However, the square of this wave function gives us the probability of finding a particle at a given instant under given circumstances. Now, as we mentioned, this wave function is a complex quantity. Complex quantity, you may have that you can represent a wave function like this. Psi is equal to A plus iota B, while A and B may be called as they are some real numbers. A and B are real numbers, psi is wave function, and you have their iota as well. Now, once you talk about a complex quantity may have both real and imaginary parts. And the imaginary part of this wave function, how to determine the imaginary part of this wave function, whenever we suppose imaginary part, see A and B are real, so they don't have any imaginary part. However, this iota, this can have real as well as imaginary. Means wherever we have iota, we will replace it by minus iota. That will give us the complex part of this wave function. Means we will have it like this: A minus iota B. This becomes our equation 2. Now, in case so we have this, the wave function which we defined as it's a complex quantity itself having no significance. However, the square of this wave function gives us the probability of finding a particle in a given circumstances, means at a given position, at a given time. And since this wave function is a complex quantity, it may have both real as well as imaginary parts. So if we define the real part of the wave function as A plus iota B, its complex conjugate will be given by A minus iota B. And this your psi square which we are actually interested in, this is actually psi star. And if you write it like this, A plus iota B into A minus iota B. So once we multiply them, what you get is, it will be A square plus B square. So the essence of quantum mechanics in any system, whether we study hydrogen atom, we study mechanics of any system, in the quantum mechanics, what we'll be interested in, determining the wave function psi. Okay, now there are certain conditions which this wave function psi must obey. There are certain formulation or the certain conditions which this wave function must obey. And one of the interesting conditions, the first one is the normalization, what we call as normalization. Now, what do we mean by normalization? Let's take it by an example. Since we discussed that the psi square is what gives us the probability of finding a particle. Suppose if we take suppose we have an integral psi square with respect to some volume integral within the limits minus infinity to plus infinity, this is equal to 0. Now, what does this physically signify? That we have psi square, we are integrating it with some volume integral between the limits minus infinity to plus infinity, and it comes out to be 0. So it means minus infinity to plus infinity is the hypothetical, these limits means we are integrating over whole space. Just take into consideration we are integrating over whole space. Whole space means it essentially signifies that the probability of finding the particle in whole space is 0. Now it makes some sense. The probability of since psi square we are talking about the probability, and these limits will signify the probability over the space. Since it is from minus infinity to plus infinity, this equation signifies that probability of finding a particle in whole space is 0. Just probability of finding a particle in whole space is 0, which essentially signifies that particle doesn't exist. It means that particle doesn't exist. Now see, we are making in fact a very bold statement there, and we are trying to understand the concept of normalization. What do we mean by normalization actually? But normalization means we are saying that psi should be normalized. What does it physically signify? We are trying to explain this on the basis of an integral. What we did is, we took a psi square, we are integrating it with some volume integral, giving the limits minus infinity to plus infinity in case it is 0. It means the probability of finding a particle over some volume interval or whole space, because these limits will indicate the whole space, this is equal to 0. Once the probability of finding a particle in whole space is 0, it essentially means particle doesn't exist. It essentially means particle doesn't exist. Now, in case we have some other integral, if we have like this minus infinity to plus infinity, if we have again this psi square with respect to some volume integral, if this is equal to 1, 0 means 0% probability, 1 means 100% probability. Now, what does this equation signify? It means the probability of finding a particle over the whole space is 1, and that's what essentially makes sense. It means particle is definitely somewhere. It means particle is definitely somewhere. So it means actually the particle is definitely somewhere, means there is 100% probability of finding a particle from minus infinity to plus infinity. So this psi square is giving us probability. Now what does this condition actually is known as the normalization condition. This is known as normalization condition. Normalization condition for a wave function means if the wave function gives us the probability of finding a particle, but the particle essentially has to be somewhere. Once the particle essentially has to be somewhere, it means the probability of finding the particle over some volume element or whole space has to be 100%. 100% means particle definitely is somewhere. So this is the normalization condition. So the first property of a wave function we try to define is that wave function should be normalized. Normalized mathematically we should have psi square with respect to some volume interval within the designated limits minus infinity to plus infinity. This should be 1. 1 means the particle definitely has to be somewhere. So psi square will give us the probability P. So you can write it this way also, integral P with respect to dv, this has to be 1 from minus infinity to plus infinity. Okay, this will give us the normalization condition. Then the another part which we will try to define here, you talk about if this is a wave function, what do we mean by well-behaved wave function? What do we actually mean by well-defined wave function or well-behaved wave function? Means what are the essential conditions where you will say that the wave function is well-behaved? The first essential condition for a wave function to be called as well-behaved is that you say that psi should be continuous. Psi should be continuous and single valued. Psi should be continuous and single value. Now psi should be continuous and single valued. It means psi, if suppose psi has two values, it essentially means that there at a particular point there are two probabilities of finding a particle, which doesn't make some sense. Actually at a particular point there has to be some fixed probability of finding a particle. It doesn't make sense that at a particular instant you have two probabilities of finding a particle. So psi having more than one values cannot be accepted. So psi has to be single valued as well as continuous. In continuous we mean, suppose if we have a space like there, it doesn't make sense that there is a probability of finding a particle from here to here. Then from here to here you don't have any probability of finding the particle. So psi should be continuous. The wave function has to be continuous, one, and second has to be single valued, because at a particular point a particle cannot have two probabilities. Means suppose if we talk about this particular point, if we talk about what is the probability of finding a particle from here at this point, we'll say the probability is 50% and 60%. It doesn't make some sense. There has to be a fixed probability of finding a particle at a fixed point, which essentially means that psi has to be single valued and it has to be continuous. The second condition, as we just discussed, that psi should be normalizer. Because in case psi isn't a normalizer, because we have to be sure that particle has to be somewhere. Once we try to integrate once we wrote the equation that we should have psi square with respect to some volume integral, this should be 1 between some integrals minus infinity to plus infinity. Means we have to be sure, in case we are interested in calculating the quantum mechanical behavior of a particle, or we are interested in defining the wave function of a particle, we must be sure that a particle is somewhere, which essentially means that the wave function should be normalized. In fact, the wave equations can be normalized by introducing a normalization constant, which can be discussed in the later section as well. But by definition, the psi should be normalized. And there is last condition for a wave function to be called as well-behaved wave function is that, in fact, the partial derivatives of this wave function, that's dou psi by x, dou psi by dou y, and dou psi by dou z, they should also be continuous. The partial derivatives of this wave function should also be continuous. So the essential conditions for a wave function are that psi should be continuous and single valued, it should be normalized, and the partial derivatives of this wave function should also be continuous. Although the partial derivatives of this wave function being continuous may not seem to be once we take a model approximation. Just for the sake of argument, if we talk about suppose the particle in a box. If we talk about the particle in a box, suppose we have a particle, there is a box, and we have a particle in a box. Now we know the probability of finding a particle outside the box is 0. Probability of a particle for finding outside the box is 0 because the particle is definitely within the box. So in case you will see these are the rigid walls. These are the walls. Now if we say, the point is, if we say are here partial derivative, will the partial derivatives of a wave function be continuous here or not? Because wave function from here and here up to this wall, it will be continuous, it will be having value, but at this rigid boundary, immediately at this rigid boundary, after this rigid boundary, the wave function ceases to exist because probability of finding the particle outside is 0. So here the partial derivatives of the wave function will not be continuous. In other words, we may say that the wave function here is not continuous or it is not well behaved. But in normal life, we don't have these infinitely rigid boundaries, which essentially means that the wave function and the partial derivatives of the wave function will be continuous and the wave function will be called as well behaved. So in conclusion, we may just define certain points. What we try to conclude here is we try to give the introductory remarks regarding the quantum mechanics, while we define that quantum mechanics is also one of the branches of the physics where we study the mechanics of a particle, we study the motion of a particle, and obviously the cause of motion, that's force as well. But the essential difference between the classical and quantum, we concluded that while as in case of the classical mechanics, we can predict the future of the particle, future history of the particle, provided we know its present position as well as the momentum consideration and the forces existing on it as well with certainty. While the same is not possible in case of quantum mechanics. Meaning in quantum mechanics, the future of the particle cannot be predicted with certainty. And the reason is because we cannot have the position and moment of a particle with certainty at present because of the Heisenberg's uncertainty principle. And in quantum mechanics, the first thing is once we say that we are interested in studying the quantum mechanical behavior of a particle, means what we physically study actually. We try to study its wave function. We try to define wave function as it's a complex quantity itself having no physical significance. However, square of this wave function giving us the probability of finding the particle. Then we try to discuss the normalization condition of a particle and as well as the conditions defining that what do we mean by saying that the wave function is well defined. While there presented some postulates like the wave function should be single valued and continuous, its partial derivative should also be continuous, and the wave function should be single valued obviously, and the wave function should be normalized as well. So these are the conditions essentially define a well behaved wave function. So thank you.